question affect the training of your model, and then your model has to, they affect the performance of your model. A change in the distribution of the functions domain or the x value distribution. For example, the x value distribution is your blue area, and then for the test data, you have a different distribution, right? So with these two different kind of distributions, your network may not be able to train because it has to relearn the model weights, and it takes a longer time to train. So how can we address this problem? We can do this by using the concept of normalization. We have the internal covariant shift. So the distribution of the input to a layer changes if you change the connection weights. This change propagates to the upper layers. So for example, this is your network, your input to the first network, and when your weights are changed, your distribution of your data might be different. So if at this point this node has the input, so it will have an effect from the next layer. So if this node had the distribution in this format, the weight distributions, while learning, red connection weights will change based on the input distribution, and after learning, the whole connection weights change, which causes the change of the input distribution. So the assumption of learning is broken. We need our model to be in the same distribution so we can have a good performance or good predictions or good classification for our results. So after the weight updates, our distribution may change. So what we can do about it? It disturbs the learning process. It slows down the learning process. So these are the two disadvantages in case of internal covariate shift. So what can we do? We can do is, for example, you have a distorted distribution. We can convert it into a normalized distribution. We can force it or transform it into another distribution. We are not making any changes to our data. We are just transforming into another normalized distribution so that our model can learn. So mostly in deep learning, we assume that our distribution of input data is Gaussian, so that it has a bell-shaped curve. Some of the properties of our Gaussian distribution or normal distribution that your the mean, median, and mode are the same values. The distribution, coincide. Mean, median, and mode values, they coincide. The curve is bell-shaped and symmetric about the mean, and the area under the curve is equal to 1, and exactly half to the left and right. Both sides have a half. So this is the normal distribution, and some of the properties of our normal distribution are, or Gaussian distribution. Let's assume that the input distribution is a Gaussian distribution. So this is your input data, 1 to D samples in total. and input into your x1 to xm, data 1 with different features, x1 to xm are input into your network. And let's suppose that this is your distribution of the value here. We know that we sum this up, w and x's, to get the net right here at this point, and then this point we have h. So at the net we have this representation. This one is your bias. So per node we will have one bias value, and sum all the weights that are coming into this node. It's a fully connected network, all the nodes, we sum them up and we get a net t. And if we do the activation like sigmoid activation, we will have an h here, right? So in order to transform this or get the normal distribution, what we do is we take the mean or the average, we know that, and then we have the variance. We calculate the variance of all the data 1 to data d. We take the variance of the complete net data set. For example, this is your data set d1 2 3 up to capital D. So this is your size of your data, and x1 x2 x3 are your features, right? So we take all these data up to D, and we take the mean and we take the variance, per feature. So if we have multiple features, we will take per feature mean and variance, and then we update our net value, the actual value, into an updated net cap value. Subtract your mean from this value, from your, for example, this is your x value, some value xi, then subtract the mean value from this and divide by the squared with your variance value to get your new x bar, and then on the x bar you apply the activation such as sigmoid activation to get your h of ti. So previously your data was represented or distorted, it was not around the mean, then moved it to the mean and did the shift and scale it so that we convert it into the normal distribution. Now all your data will be centered around the mean, and your model can now learn better. So all the data that we come here, all the values, for example x1, it will be updated as x1 this, x2 it will be updated as x2 this, and so forth. All these features, xm will be converted to xm this, and now our data x1 cap, x2 cap, xm cap, these are the features in your sample d1 di d1. All these samples will be updated, all the one by one feature, and then we can have this representation for each separate feature. Batch normalization, you are calculating the, what we have done is we calculate the average and variance of the whole training data. It can be inefficient, so because, for example, our data set size is this, or 6, 10 raised to power 6, 10 raised to power 5. So calculating the mean and then average, it's not that it could be inefficient. So why not normalize the inputs with respect to each batch by batch. So our data we discussed before, this is batch 1, batch 2, batch 3, batch 4. For example, each batch has a size 64 take this batch, take the mean variance, mean variance, mean variance, mean variance separately, and then normalize your data. This can also be done. And next, what we can do is we can use the sigmoid or the tan h as the activation function. So nearly the behavior of sigmoid around 0 is almost linear, not actually linear but almost linear. And then we add the linear transformation after normalization. So what we are trying to do, why we need sigmoid or tan h transformation after the normalization, so that we get rid of the non-linearity and our network can train better. So we are again considering a normal distribution and Gaussian distribution. We have our training data, different batches are given as input. Let's suppose this was the distribution of net I here in batch B, and then for this batch we calculated all the samples, but per data batch, if we are doing is, for example, batch 1, then this will be D is 1 to D1 batch 1 net DI. So for batch 1, only take this batch, find the mean value, find the variance and update according to the batch, and then transform. In our model, what we will do is it will learn these two parameters, the gamma and beta. These are learnable parameters. So per batch we will do this transformation and find the mean variance to normalize our data, and these are basically used. So our network has to learn per batch these two parameters, and these are the learnable parameters. They are basic, nothing not so difficult. They are just the shift and scale. You can say them, they are shifting and scaling your actual input and then taking your sigmoid or your activation. So in a neural network without batch normalization, we have the input layer, we have the hidden layer and the output layer with these weight matrices. But in our batch normalization, we will have the input, then we have batch normalization layer, and then we have the hidden layer, and finally your output layer. And the network has to learn these two learnable parameters per batch. It has to find what are the most suitable values for lambda and beta, so that all the we can have a normalized version of our data for training the network. So here we have the generic representation of data is coming from different nodes into node I. So first we then find the net, and then we take the activation. But here in this we have network, we have the weights here. We calculate per batch first the net, then we calculate the batch mean and variance, and this is mean for the batch, variance for the match, and some error. And we have a net I for this, and this is given an input here to get our output y, which is actually a scaled version and a shifted version of our actual net, and then it is given as the activation into the activation to yield our actual output, which is H, hidden layer output. Another graphical representation of our data input layer, then we have the nets, we have the H, we have error, then weight updates are applied, backpropagation. So this is how it is working in normal case. We already know too much about this now. Then we have the batch normalization version, where we have first your x, then we have a net, but here we have an update which is based on your batches, and then it is updated to obtain your age, and these are the learnable parameters here for the backpropagation, like gamma and beta, and your W weights. They are updated per batch. This is the general algorithm for batch normalization. Normalize each batch by both mean and variance, and for each node, normalization is performed independently. Value of x is the input over a mini batch, x1 to m. Parameters that we are trying to learn are your gamma and beta, and you are finding the mean, mini batch mean and variance, then normalize, and then scale and shift to get your yi, which is your desired output. And our network will learn these two parameters, gamma and beta. We know that for training, the mean and variance of each batch are used for normalization. So what about at the test time? At test time, we don't have the complete data set. We don't have like 100k samples. We don't have like 70k samples. For these 30k samples, we cannot. So what we can do for at test time, which mean and variance should we use? That's the point. What we can do is we can use those that were used in the training. Of course, we would have, during the training, we would have obtained some mean and variance values, so we can store them. And then this is your test that assemble, and you obtain your net function. And then you have an unbiased estimator of mean of the population and mean of the unbiased estimator of variance of the population that was done in the training. B is the number of batches and M is the number of samples in each batch. So you can do this transformation. Okay. Mean per batch. Then we have per batch, then you can find your variance, update your variance values to transform your output net and obtain your gamma and beta here, and finally apply your activation function. So we use those we have obtained in the training, at the training time, those variance and mean values we can use at the test time using these two equations. It is very simple. So what is the advantage of batch normalization? It is that we reduce the internal covariance shift and reduces the dependence of gradients on the scale of the parameter or their initial values, and regularizes the model and reduces the need for dropout or photometric distortion, local response, normalization, and other regularization techniques. So dropout and regularization, and normalization, batch normalization, these are some of the techniques that we can use to optimize the training of your deep neural networks. Here is an example of batch normalization. So without batch normalization, we have accuracy, you can see in the dotted dashed line, as the number of samples are increasing. So the accuracy increases, but we can see that with batch normalization, at the very beginning, even with smaller size of your data, we can still have a good performance. And this is your performance without batch normalization. And then we can, at the beginning of the training, you can see that the network will perform it will not perform so good, but with normalization we will have a good performance even at the start of your training. So your input distributions are now normalized to give you a better output. So what are the key advantages? Of course, learning is faster because the data is now well distributed. The distributions are much more representative and there are less variations in the distributions, so our network can learn much faster, and it is not stuck in the saturation mode. And even if we don't use Relo activations, we can still have a good performance. And we have high accuracy. Why? Because flexible on data distribution in every hidden layer. So we can have normalization, add no normalization, batch normalization in each layer. And we can see with batch normalization, our error is obviously reduced as compared to our network without batch normalization. And learning rate is set to 0.02002. So deep networks, they do have a strong power, but they may be prone to some problems, and we have studied some of the techniques that we can use to address these problems. First is your high complexity. So we convert them into simpler structure. They are hard to optimize. So we focus on mini batch gradient descent and use other activation functions. Overfitting is a very common problem. So we use a larger side of data. Then we have various regularization methods, L1 and L2 regularization. And then we have studied the dropout concept in detail. And in order to address the internal covariate shift that we have another problem in training the deep networks, what we can address it is with batch normalization. These are the lecture contents that we are going to discuss today, and we studied various techniques to improve the performance of our deep networks. If you have any questions or queries regarding the topics that we have covered today, you can send me an email